and keep the whole thing going. This is a new guy to audio. He just started. His name is Nelson. What is it? It's yeah. There we go.
Careful with the microphone.
And he's going to talk about something about v-fets. They're Dutch. V-fets. So, Nelson, pass everybody.
Thank you. All right. Does it sound good? You can a little louder.
Always.
Me? Am I not amplified, or am I supposed to?
You're not amplified.
Oh, okay, I get it. All right. But I got two screens. I'm good. So I had some stuff left over from last year that didn't happen. So the first thing I thought I'd do is like launch off with that. So this is in 3 parts. And I've got all the time in the world, so if you like, what we can do is through each part I could stop and answer questions. And if by chance you have a question that really probably ought to be said, just go ahead and raise your hand and I'll try to catch on and deal with it, because it's all laissez-faire. I talk by stringing pictures in a row and then filling in the blanks with some dialogue. Part 1, the 2SK77B single-ended v-fet amplifier. Anybody who's followed what I'm doing pretty much knows that I've been playing a lot with v-fets, also known as static induction transistors. These are semiconductors that are kind of special, and mostly they're special because they resemble the equivalent of what would be a triode if it was a tube. Almost all the FETs that we deal with in day-to-day existence look like what we think of as pentodes. They have different curves, triodes and pentodes, and the v-fets, or SITs, and SIT stands for static induction transistor, awful name, is got a different character than the regular FET, and this is something that is worthy of exploitation when you're trying to do audio circuits. There's a different character, there's a different sound. It's pretty interesting stuff. Let's see. 1975, I think, just about. At the behest, it would appear, of the Ministry of Trade of the Government of Japan, Sony and Yamaha released what were known as v-fet amplifiers. V-fets were originated in Japan, and in point of fact, there was a certain amount of national pride associated with this, rightly so. The v-fets from Sony and Yamaha were marketed for something in excess of 5 years, and then kind of slowly went away. But probably one of the most premier of these amplifiers that came out of that era was the Yamaha B1. That's this guy, probably the most
Although that's a Yamaha.
well, I'll be damned. I thought it looked like a Yamaha at that. All right, well, it doesn't matter, does it? Sony did them too. I have talked about the Sony stuff before. Tonight we're talking about Yamaha. Here's a 2SK77. This was a v-fet part that was, at that time, the biggest guy of the bunch. It comes in a supersized TO3 package. It's big. It's rated at 200 watts, a couple hundred volts, lots of power. It's an absolutely spectacular part. Getting them is virtually impossible at this late date. But it has a character to it which looks kind of like a triode. If you apply various control voltages to its control pin, that's these sets of curves, and these are the voltages from gate to source on those FETs. You see that it does a certain amount of current in amps, quite a few amps really, and quite a few volts. And if you change the voltage, you change the amount of current. But unlike the other parts that you normally deal with, the amount of current going through them is very dependent upon the voltage across the device itself. What would be maybe the power supply or the signal swing. And they are very different, and later you'll see an example of the opposite. But because they have these lines, as opposed to having a flat characteristic that goes horizontally, they behave like triodes. They also respond differently to audio. They have a different sound to them. And in audio circles, in high-end audio circles, this is a very much desired character, much in the same way that triodes are a very much desired character if you're building tube equipment. Not perfect for everything, not made for every application, but it's got its spot, and this is the place. This is the simplified diagram, and I say simplified, of the Sony B1 amplifier. Those of you who don't follow schematics can just ignore what I'm about to say, but basically it's simplified down to the following. These things are all current sources, constant current sources, here, here, and here. All they do is just feed constant current no matter what happens. There's an input differential pair of, by the way, v-fet input transistors. They drive a differential pair of voltage gain transistors, which are also v-fets, little ones. They're cascaded by a set of v-fet differential transistors. They drive another set of differential gain transistors, which are basically cascaded by this set of transistors, and then they come to drivers, complementary drivers, which are v-fets, and at the output of this thing are giant 2SK77 power transistors. At the time, this was the only all v-fet amplifier that I'm aware of. In the old days, when you look at a lot of the stuff that both Sony and Yamaha did that were apart from the B1, they mixed other kinds of semis in there as well. In this case, though, this was pure v-fet all the way. Well, it was actually more complicated than that. That's the real schematic without the values on it. And as you can see, there's lots of parts that have been added on that I left off when I was trying to give you like a simplified picture of it. But this is the actual schematic of that, and you can still see here's the output transistors, but this is all bias circuits and constant current sources. If you strip it away enough, you go back to this. Now, this is a very complex circuit. In the 70s, they were into complicated circuits, maybe because they could show off in that regard. There are still plenty of examples of complicated circuits out there. I like to show off by having simple circuits, and if for no other reason, then it's a lot easier for the do-it-yourselfers to build, and easier for me to build for that matter. This is the 2SK77B. This is the successor to the part that we were just discussing. This thing was made by a gentleman in Japan who I understand had made a very large amount of money in the software industry, and he decided that, first off, he was crazed about hi-fi, and he decided to put up the money to have what apparently the original people who built the 2SK77s and perhaps even the Sony parts. That company's name is Tokin, T-O-K-I-N. He contracted with them to make a bigger, newer, even beefier version of that part. This is it. It is rated at 300 watts and a couple of hundred volts. It comes in a big hockey puck. It's a totally amazing transistor. And of course, it's kind of difficult to get a hold of because the guy who commissioned them had his own amplifier company called Digital Domain. He released a very nice product, one that I wish I had a copy of, which was, for all intents and purposes, a redo of the original Yamaha B1 amplifier. And and I don't know anybody who has seen one outside of Japan. However, one fine day, I got a nice email from a gentleman who represented FAL, it's a speaker company in Japan who makes Heil tweeters in Japan and also square woofers. If you go through the pages of Stereo Sound magazine, you may in fact have seen some of the stuff that he does. He had obtained, actually, the email was, we are presenting you with a very great gift. And when the gift arrived, it turned out to be quantity 20 of these parts. And some square speakers and Heil diaphragms and stuff too. It was very generous. So I have in my possession 20 of these parts. And I also had some subsequent discussions with the gentleman in Japan. And he thought that he could obtain several hundred of these parts at a cost that was approximately $400 a piece. I unfortunately really just couldn't stretch myself. Having spent all my money on my own SITs the year before, I couldn't stretch myself to pony up the amount of money that he needed to get them to me. However, I did not send back the 20. And we can all thank him for his public donation here, because otherwise we wouldn't be playing or even being able to think about this, and you'll see where I'm coming from. Unfortunately, Token, who made these things, suffered during the big earthquake in Japan. I understand that the fabrication line was destroyed, and I understand also that Token did not elect to spend the millions of dollars that it would have taken to put it back together. So now those are what we call really new old stock parts. So I believe that some of them are besides Digital Domain, who is a gentleman who makes these. I'm not sure if he still makes them or not, because they don't call me up very often, and I don't speak Japanese. But they also seem to be possibly some of them in the hands of a company in Japan called Maxonic, which you can, I think that's Maxonic. You can Google them. They have some fine-looking v-fet type products, and it looks to me like they are fairly bright. They are not the kind of complicated circuits that I showed you earlier, and in fact, one of the beauties of these sorts of parts is they give rise to designs that say, just put me in there with a power supply, I'll take care of everything else. And in fact, that's why they're so desirable. Now this one, the 2SK77B, looks a lot like the 2SK77, except that the numbers are ramped up even higher. This is a 300-watt part. What does that mean? Well, it means you can build a pretty powerful single-ended SIT amplifier with them. I will contrast this with my own parts that I had made in Mississippi some years ago. Mine are 50-watt parts. These are 300-watt parts. I build 10-watt SIT amplifiers with my parts. These things, 50 watts is nothing. It's easy. And so we move out of the category of being able to build some solid-state equivalents of what we think of as single-ended triode type amplifiers, but rendered in solid state, out of the 5-watt and 10-watt basement into the big time. The other thing about it is the curves on these, the way they are aligned, give rise to some interesting characteristics. The distortion is quite low compared to the smaller parts. The damping factor, the intrinsic damping factor without any feedback on a MOSFET or something is hundreds and hundreds of ohms, so that the damping factor is like non-existent. On these, on my SITs, the little 50-watt ones, I get damping factors of 4 without any effort at feedback. This gives a damping factor of, my damping factor is like 2, it's 4 ohms out. This thing is like less than 2 ohms out, damping factor of 4. So also they have less leakage and they're quieter. These are really nice parts. So of course it became time to build an amplifier with them. This was last year, and I was prepping for this event. Here's what we got. Here's a 2SK77B. Its source is grounded. It's operated in common source mode, which means it has voltage and current gain simultaneously. It's got an input. It's got a little voltage supply that sets up a bias for this to put it in the right spot. In other words, everything's got to be at the right DC voltages to settle into the points that I want. And this guy is just for protection, because I know guys who can blow these things out with their prototype tubes that have no output caps. And this is just a little bias network. It comes in, there's an input cap. This guy is here to just keep the thing from flying away due to either self-oscillation or anything that might come in as antenna-wise. Up here is all this is a current source. There are designs where, in fact, it could have simply been a big fat resistor. If you look at the circuit for a SIT1, you see that it is, in fact, a big fat resistor. That was kind of the charm of that. But I'm really going for the power and the glory here. This is a 300-watt hockey puck made by Ixis. It's a big-ass MOSFET. It's as nasty as this guy, but it's a classic MOSFET. We're only going to use it for a current source. We're going to set it up. It's going to be biased by an opto-isolator, because this whole situation with this circuit here and this attachment sets it up so that through this set of resistors, you're going to put 1.1 volts across them, and it's a constant figure. The speaker load, which is capacitively coupled, can tap into one of 4 points along this chain of resistors. If it taps in down here at point A, in other words, if this arrow is down at point A, then this whole thing is merely a constant current source, a device that doesn't care what the voltages are on the signal path. It always delivers exactly the same amount of current. Now, it's not really constant, but it's good to about 200 ohms or so, which in the scheme of things here is plenty good enough. However, as you tap up, you give this circuit some gain, and this circuit, as it starts having some gain, that is to say, having some contribution on the part of the top transistor, it becomes what we've referred to in the past as a mu follower. It is an active current source which ghosts a portion of the output current. It is used. It's there to. You can use it to tailor the distortion figure. You can use it to alter the gain. You can change the efficiency a bit. But in the end, the biggest thing that it does is it allows you to swing twice as much current if you want. And when we're starting to talk about kicking some real power around here, that's a good way to do it. Now, I've set this up as taps. By the way, all this stuff is going to show up online, so you don't actually have to take notes. And I will, you can be exposed to it, but if you want to follow up on this, it'll all be there. Okay, so I built this thing. This one here, it's got a 60-volt supply. I'm running 3.5 amps of current through it, which is quite a bit. So it's drawing a couple hundred watts. And it needs a nice big heat sink. And if you set that up and you look at the various settings of these guys, the taps that I talked about, this is the distortion versus output power. You can see here it's basically clipping at 50 watts, maybe a little bit less depending on the settings. And I have 4 colors here. They represent, we got A, B, C, and D. When you look at them here, A's at the top, so it's A, B, C, and D here, and they are the distortion curve versus power for those 3 settings. If you do this thing with the A curve, which is the constant current source, you get the largest amount of second harmonic distortion as part of the character of the product, and you're in at about 1% at about 10 watts. As you go down with more gain on the current source, you can get better and better figures. Finally, when you get down here to the aqua, you're starting to get really low distortion, relatively speaking, but you're starting to see more third harmonic and less second harmonic starts coming into the mix. For practical purposes, I ended up choosing for the design when I actually want to listen to this myself, I go with the deep blue one, which is it's actually the middle road point. I'll go back. It's tapped in here, where there's 0.2 above that point, 0.2 ohms below that point, and so they're actually equal value. That sets the gain of the mu follower at a little less than 1, which is nice and conservative. So there's that. This amplifier's got quite a good characteristic for frequency versus distortion versus frequency. And you can see here it's essentially flat at whatever value it is. So it's frequency independent. That's nice. This is one thing that always has to be considered with a design like this. When you are driving a big fat transistor like this, you are into some capacitance on its input junction, and you have to have a relatively low source impedance that you're going to drive it with. I have designs where in the past I have simply buffered that with a FET, or you can get a preamp that can drive some, have a low output impedance. Here's the frequency response of this circuit with a 600 ohm source, showing it rolling off, it's rolling at 20K, it's down. At 25 ohm source, it's down a decibel at 200K. So you can get lots of bandwidth out of this part, but you need to give it a low source impedance on your preamp. What this means also too is that the input impedance of this circuit is actually high. In this case, I've set it at 10K just by putting a 10K resistor off to the bias portion of the circuit, but it starts dropping off. And so, for instance, at this point here at 20, 30K, it's about 600 ohms. So whatever's going to drive this at high frequencies is going to need to have the ability to throw a little bit of current at it. Now, I make preamps professionally that do just fine in that category. There's plenty of stuff out there. However, you're not going to drive it off of the plate directly of a tube preamp. But an audio researcher, a CJ, will do it, as will a lot. So, but you have to keep that in mind. It's a little item. Okay, so that's part one. Do I have any questions?
Could you speak just a little bit louder?
Maybe I should just come over here. I'll point at you a lot. How's that? Yes. I'm sorry?
Have you tried to same a similar amplifier with an ALF current source?
I can get essentially the same results. You could do it with an ALF current source very easily. I've kind of. He was asking if you could do that instead of using the mu follower, whether you could use that with an ALF current source. And the answer is sure. The mu follower is actually just a little easier, a little dumber. I like dumber. Yes.
Yeah, in the original Yamaha, Sony, whatever design, why do you really need 3 diff amp gain stages in a row?
Oh, is that only 3? I'm not sure. It might have been more.
Okay.
Well, first off, you got to remember, in the mid '70s, we were engaged in the who's got the lowest distortion and the highest slew rate and long list of marketing things that were driving the marketing departments, and I don't know who designed these circuits, but my guess is that they had bosses, and their bosses had to listen to the marketing department, and these were the things that were wanted. Now, it looked to me like, interestingly enough, later on, some years later, in Sony products, they were still using the SITs, but because they were what known as depletion mode parts, they could self-bias themselves. They were being used as the non-audio circuit cascodes for bipolar output stages. And you go, well, what? Why would you use SITs to cascode bipolar output stages? I mean, it seems like a kind of a misuse of the parts. My guess is there's a good chance that somebody was instructed to use them anyways, and they found a spot. I don't know, but this was the age when people were they were getting excited about a lot of issues, and they were beating specs into the ground. There are still examples of that. Every time a new technology comes along, I'm of the opinion that when a new technology comes along, the first thing they do is they try to make it as perfect as possible. And then after they've more or less achieved that, then everybody else is free to make art out of it. And that would be me. So why is it so complicated? It's like for the same reason that they were all so complicated.
I mean, the kind of gain you need from those 2 points is like what, 5, 10, right?
Well, I get 20 dB off of the part itself.
Yeah.
That's enough.
Exactly.
in my book. But you see, I don't get a really huge damping factor. I don't get really huge incredibly low distortion numbers. What I do get is distortion numbers that are achieved without feedback, and also it's second harmonic character, a little bit of thirds mixed in there. I wouldn't take and point this at a very inefficient speaker and hit Symphony Fantastique and try to knock down the house. We all know little amplifiers are really good at, and here we are. This is a little more powerful than the average that we've been dealing with. It's a fine example of some place where we can make some progress. Now here's the rub is, I'm sorry, more questions. There's still some?
What sort of, how would something like this be in a push-pull configuration? Would that not?
Oh, it would kick butt.
Yeah.
Yes, indeed. I mean, that is what the original B1 was good for.
Yeah.
And for that matter, the digital domain circuit is a push-pull amplifier. It's a beautiful piece. When they came out, you could get them for $10,000 a pair in Japan. For all I know, you still can. I don't know. Nobody I know has actually seen them. I know that they are in Japan. But as to I keep in mind that the guy who developed them and brought them out didn't need the money. So I don't know. But yeah, no, I mean, you take a 300-watt part and run it Class A, B, push-pull, and you can just go to town. There's no question you can build a very powerful amp.
Even harmonic distortion is canceled.
You can get excellent cancellation.
Back to part one of your amp design. Would a cathode follower stage be adequate to drive that
Yeah.
for the amp?
Yeah. Your standard, not
Like a 6 DJA.
Yeah, I mean, like I say, look at what Audio Research or CJ traditionally had for cathode followers. That'll drive it. Yeah, and you have to remember, there's not truly a lot of energy up at 20K. It's not something that you have to lose any sleep over. It will simply get lost in the capacitance, and it won't create any excitement. So it's not that much of an issue. Small. Now, here's the rub. Oh, more questions? Any? Okay. Here's the rub. I got 20 of these. I hope I still have 20 of these. I don't know anybody else who's got some. Somebody in Japan has got a hold of these. The 2SK77B, if you can get any, count your stars as very lucky, and I actually hope that you know. Now, by the way, I have to mention that, people go, well, you give so much to the DIY community, and I go, you don't understand that I get more back than I have to put out. And one of the examples of that is people going, Mr. Pass, I found some of those parts right over here. And I'm going, whoa, thank you very much. And this was a fine example. Actually, the ones that I had made were because I got connected to Semi-South because somebody posted on DIY Audio, guess what, Mr. Pass, there's some v-fets being sold by these guys. Have you seen that? I said, no, I have not. Thank you. All right, so right now those are pure unobtainium. I'm going to be able to make a few channels and that's over with, unless somebody finds a stash in Singapore like we did with the Sony parts a couple years back, where we ended up with a couple thousand pair easy, and I think I've got 400 pair of those going into kits that are going to be available at DIY Audio. In my secondary room, I've got a little system running, and I've got the Sony DIY amplifier on display playing. This is the one that we this is the design that we are doing for as a DIY kit through DIY, so that you guys can build these, because I want these things built. And it's a mini version of the ones that Past Labs did for Sony, where we did the Sony 40th anniversary commemorative amplifier with tons and tons of them and big heat sinks. Very nice amplifiers. These are little 20-watt versions, but they sound really good. You can hear one in that display. But the problem remains, well, what about this higher power v-fet deal? Because once again, I'm not telling you about I'm not telling you about this guy so that I go, well, haha, I've got some, and too bad for you. That's a preface to this, which is we can build something really very much like it, and we can get the parts for about $14, and they're at Mauser and they're at DigiKey. This is typical of what we're going to be able to use. You can use a number of different parts that will fit this bill, but the point here is that this one costs $14. It's in stock. I checked it out. It works great. Okay, and we're going to embark upon it. Now, this is the one that I think you're going to want to build. Now, I told you earlier about the curves, the lovely curves. On the left, you got your triodes. And you see how that looks. The family of curves curve up. Now, I guess that's why they call them that. Curve upwards. That's at 300B, by the way. The SITs and the v-fets, they look like that. All the other MOSFETs and j-fets and stuff that we pretty much deal with, they look like this. They're curved in the opposite direction. Now, in many applications, this is a very good thing. Again, this is a specialized usage. 90% of the time, when somebody's designing with MOSFETs, they want this. In this case, we want a particular sound, want a particular characteristic, and we're shooting for that. And it's reflected by curves that look more like those guys. This, I stole this right off the pages of DIY Audio, cut away all the serial numbers and stuff so that I wouldn't get in trouble. This is a guy who ran up a nice little quick circuit simulation of what is known as SHOD feedback. Now, actually, SHOD feedback is actually something that was documented by Harold Black in his original work when he invented feedback in the 20s. But later on, some years later, when some people were probably whining that pentodes weren't as good as triodes for some reason, he goes, oh, well, that's easy. And without necessarily having reference to Black, he said all you have to do is put a little loop on them like this. And in this case, we're doing so with a MOSFET, because a MOSFET looks like a pentode, and that means it looks like this. Here's the MOSFET hooked up, got a little battery, and it's going to send signal in, and here's your load. And this is what the output off of the drain looks like. It's a series of almost flat curves. It's not ideally flat. But if you throw a little bit, and this is just an example in a simulation, but if you throw a little bit of what's known as SHOD feedback, and it's got his name on it, even if Harold Black invented it, common phenomena, you get those other curves, okay? You get the triode character. Well, where are we? So this is what SHOD feedback looks like. Usually it's discussed in terms of tubes. They go, okay, you take a resistor off the plate and you bring it down to the grid, and you have another resistor in series with the input, and what you get is you get a triode curve off of your pentode, and you should be a happy guy. Indeed, most tube guys don't have a need particularly to do this because they can buy triodes. Most of the time, though, you can't buy a triode semiconductor, so you're kind of stuck. However, the question here is, to what extent is this approach usable for a MOSFET circuit to simulate a triode action, more to the point, to simulate a v-fet? Well, I decided to explore that as a serious thing because I discovered really realistically I wasn't going to get any more than the few handful of parts that I had also. the idea is simple enough. This constant current source is just there to provide the power. You got to capacitively couple the output to the load, otherwise there's some DC on the load, but we can ignore that. And you just use a circuit like this to drive that input, and the negative feedback aspect of that has the same character as what's known as the drain characteristic of the v-fet. Works like glue, gives you pretty much the same sort of set of curves. Not truly identical, but good enough for government work. With that in mind, oh, well, wait a minute, let me go back. Downsides to this. Well, there's one. If this is a fat part, this has to be a relatively low resistance value. Remember I showed you how the bandwidth goes to hell if you're running 600 ohm source impedance on this circuit. Well, okay, that's a problem. And not only that, but this sort of circuit, shod feedback, lowers it even more. So now we have a situation where you've got to have really quite low impedances, and to make this guy work, if this were a big power transistor, to make this work, you would end up driving it with another amplifier. It would still have that character, but you're driving it with another amplifier, you know? Not that satisfactory. But there is a trick. I'm not sure. I may have invented the trick, but usually I discover that every time I think I've invented a trick is somebody else has actually already thought of it. But whoever they weren't smart enough to make it public enough for me to know about it, so it's my trick. And here it is. This is my standard Jensen transformer. People go, why do you pick that particular transformer, or for that matter, why do you pick that particular capacitor? Because I got a drawer full of them already. And so you'll see the same old values used everywhere. Why? Because I got tons of them, and why should I use anything else? This is very similar to what you saw before. This is the same circuit that you saw before when I was describing it with the 2SK77B, okay? Except that I've simply consolidated the 0.2s out. Instead of 4.1 ohm resistors and tapping the middle, I've decided I'm just going to use a couple of power 0.2s, and there we are there. So that's the same circuit as before. This is all the same, except that I have a feedback loop coming here off of the output, and it goes back, and I have an input transformer driving this, and I use the input transformer to process the output versus the input. In other words, to make that same set of comparison that we were trying to make with its predecessor. This is feeding back, and a comparison is occurring right here between the input and this circuit is doing exactly the same thing, and then it's doing so at the primary, and that the secondary system is then driving, as secondary to the transformer, it's driving the FET. Why do you do this? Well, first, it works fine. It processes feedback. In fact, I have, if you look at F6 is another example where I've used a transformer as the thing which processes the feedback loop instead of an active circuit. There's some limitations to these transformers, but they're really fine transformers. It's not like they're much of a problem, and they're used in the recording industry extensively. Nice transformers. The thing about it is, and there's a reason why you do this. One is, interestingly, it corrects the phase of the output, so the output's in phase. You don't have to flip the terminals on the loudspeaker, but that's trivial. The big thing is, this feedback brought back to this junction raises the input impedance instead of lowering it. So what we have now is something that implements shod feedback, but instead of taking the output impedance down close to zero, it multiplies it dramatically. So now you have a fairly high input impedance for the circuit. You still got to be able to drive that capacitance, whatever it might be. But you can now, you won't need you won't need a small power amplifier to drive it. You can send it off of a regular preamp like the tube piece we were talking about before. So what we've got is a pretty decent simulation of a SIT. Long day. It's a pretty decent simulation. And it's got the same variety of second harmonic to it. It gives us the same kind of damping factors, same kind of gain, same kind of pretty much everything, so that if I didn't know and I had to just look at it on a scope, comparing the two, I wouldn't necessarily be able to tell which one is which. So this is a totally legitimate circuit, works like glue, and at some point you can just take it as is. The other notes on this, I did test this with a mid-tap as shown, and I also tapped it as a constant current source, so I got to see a couple of things. The mid-tap gives me a damping factor of 12. Over here, using just a constant current source, the damping factor was 7. The input impedance was 5K, and it was 600 ohms from the capacitance at 20 kilohertz. It had an open loop gain of 38 dB, and after I apply 18 dB of feedback, it had a 20 dB output gain. Essentially, the same kind of figures that we got off of the Yamaha, except that the damping factor is a little higher. And as we go a little farther here, we see pretty much, and these are the two tap figures. We see that we pretty much got the same kind of distortion characteristics versus the Yamaha. The waveforms are pretty much the same. You look at them, there's the second harmonic, maintains the same phase relationships between second and the fundamental. The distortion rises a little bit at the top end. That's the transformer as compared with the original one using just the Yamaha part. And frequency response against various sources. I've got a 50, a 100, and 200 ohm source, and at 200, it's 1 dB down at 20K. So you can get by pretty easily with a 100 ohm output impedance for a preamp. Well, I happen to make preamps that do just about that, or I even have some fancier ones that go lower and give you a little more bandwidth. It's got a little bit less bandwidth than the maximum we got out of the Yamaha part or design, and the reason for that is the transformer itself has got a little bit of roll off at 200K. Let's see where we are with this. Oh, okay. So that's that. You can get the parts. It's a piece of cake. Same 60 volt rails, same 50 watt rating, same kind of distortion specs and curves, a little bit better damping factor, but you can build it. That's the real key here. So this, as far as I'm concerned, is a real thing that you should rush out and acquire the parts and go ahead and do it. Take my word, it'll be worth the effort, and it won't be actually that costly. Again, I paid $14 for those transistors, so that transformer, by the way, is $29 or so.
Now, so how much dissipation are we going to need just in terms of heatsink per channel?
Well, that's 3 amps at 60 volts, so it's a little over 180 watts worth of heatsink.
All right, we're going to need a fan.
Well, I'm just going to bolt it into the interior of one of the .8s, and it'll be just fine.
You've got heat sinks that big.
Yeah, well, heat sinks. Think about it. We got heat sinks. I mean, the thing about this crowd, I know, and it's been my discovery from many years back, is that about half of you are more comfortable welding and machining than you are soldering transistors, and so I personally just think that you can just have at it and build some big hardware. We all like our big hardware, anyways. Any other questions?
It doesn't seem like it would be that hard to drop that into an F6 topology.
As a part, I think you could. You might have to screw around with it a little bit to make sure it's stable and happy. But yes, anything that you see here, you could do with a push-pull easily. Anything else?
You wouldn't need to match the devices?
No, in this case, the current source on this is already under control with its own little control loop, and that's not even much of a loop. It's actually a form of degeneration across those 2.2 ohm resistors, but it's relatively tightly controlled, so its character doesn't really come marching into the situation. So you actually don't need matching. you can match them. It might be the tiniest bit of difference. No doubt everybody here will hear that. But I haven't matched these parts in practice.
How much dissipation of the current source?
Same as the other, which is half of 180, about 90 watts. Now, when you go through the catalogs, by the way, you're going to start seeing something new. In the old days, you looked at a power transistor and it'd say 150 watts. And when you looked at what it could do at DC dissipation at a given case temperature, you'd look and the voltage and current curves would intersect at, oh yeah, that's 150 watts. Now when you go through the data sheets, they'll show you transistors that say 1,000 watts. The only problem is that they're talking about their uses as switchers. And if you go and really trace what the DC dissipation figure might be, not the figure for a hundredth of a second, but for a second or more, you'll find that you're getting down into that 300 watt, maybe 400 watt zone, even for these big hockey pucks. So when you think about these things, if you go, well, I know guys who do this, I'm going to scale it up. I'm going to make a kilowatt amplifier because I've got transistors that are rated at 1,000 watts. Take a close look at that rating because the way the industry has come to look at these is now different. There's 1,000 watt transistors that you can burn up at 300. So just a little caveat, because these parts here are an honest 300. We're running them at 100. They'll last a good long time. Anything else?
Is there anything intrinsically difficult about making the SID type transistors? Is it just a matter of scale and cost?
I think they're intrinsically difficult to make in terms of getting them right. As I understand the story about the 2SK77Bs out of Japan, the Token actually went and got the guy who did the originals because he was the most skilled. And there is a skill set that comes with this. I mean, and it's not always easy to duplicate somebody else's work. A good example is the effort that Linear Systems has had to go to come up with 2SJ74 comparable parts. Not trivial. Well, Toshiba managed it. They had some genius once upon a time, or some team of people who worked on it for years. I don't know, but they had the process down. I would say that if the guys at SemiSouth had had more years to play with the SITs that I got from them, while I'm perfectly satisfied with what I've got, I have no doubt that they could have been made more extravagantly better. The 2SK77B is that sort of part. They went back to the original source, is what I understand. And no, they're not trivial to make. The other thing about it is that as far as I can make out, you understand that the primary use in the real world for SITs is radar and satellite. And that means big companies and government agencies. You don't see the parts in the DigiKey catalog. But they're out there, for sure. Yes?
Can I drive a small electrostatic?
I don't see why not. There's nothing that's going to break that part. As long as you put that little protection diode on the input that I got, and even that's only for guys with tube preamps, you know. Part 3. Okay. Like I said, I'm a magnet for stuff. And a few weeks back, a guy emails me from Denmark. Hi, my name is Frank. I've got this great full-range loudspeaker, and I need to have somebody to play with it and maybe introduce it to people in the United States because I'd like to make them. And so, you know, how about if I send you a pair? And I went, of course, send me a pair. I love that. So he did. And this is what he sent me. This is a 6.5 inch full range. It's got a honking big magnet on the back. In fact, the cutout for the rim is the same as the cutout for the magnet. It's kind of like some of the big Fostex series that we've seen as the special editions. big magnet. This guy's actually into field coils, and he's working the field coil thing, but to get this thing out the door and get it tested, he arranged for it to be given a ceramic magnet to begin with, but it's a large one. This is a 6.5 inch cone. I have them mounted up in a pair of Matasound 3/4 foot cubic inch boxes, sealed boxes next door, and you can take a listen to it. They're just I have tested them in open baffles, slot-loaded open baffles, and this little sealed box. I actually, considering that I had this little nice small room this time, I decided that a sealed box might be just the ticket. In fact, when I hook this stuff all up at home first before I bring it here, believe me, and it was just like, wow, this is like 2 days ago. This is really great. I think I'll just take it in the box and we'll hook it up, and there it is. Now it has there's no equalization, there's no treatment at all. But I will show you that there are some areas where it might be of interest to do so. I also successfully ran it in just an open baffle on its own. It actually had bottom end. I was surprised. And I put it in my slob, the slot-loaded open baffles, and it took a lot of trouble crossing it over because of the bass response was extended on this, and I'm not used to getting that. But I worked that issue out too. But actually, if you just need a nice pair of speakers that your wife will let you have in the living room, this might be a candidate. This black cone is apparently spun glass. That is to say, it actually looks like paper. If you look at it, when you look at Lowthers or some of the other like Feastrex, or I have Moths, instead of being a pressed cone, it's been cut and then bent and folded into a conical shape and glued, so you find a seam on it. I think there's a seam on the whizzer. It's got a whizzer. That's a phase plug there. The phase plug is more handsome than it looks there. And there it is, though, mounted up in this box. I ran impedance curves on this thing. The top blue one is a free air resonance. Okay, this is calibrated in ohms off to the side versus frequency. Its resonance is about 53 hertz. Then in that box that I just showed you, the 3/4 foot cubic foot box, I have two curves. I have a green one, which is the taller than the little red one. They're both at just a little over 60 hertz. The green is with no stuffing in the box, and the red, is that red? Yeah. The red is with some stuffing in the box, and in fact, they're on display with some stuffing in the box because I like the sound better that way. But that's the characteristic. If you look at that and think about it, though, or if you get the measurements, it's a fairly high QTS on this. I would guess it to be 1 or maybe slightly higher than that. So it's got a little bit of boom to it. However, it has. That little characteristic seems to serve it well in this application. Here is the response of this loudspeaker at 1 meter and near field, and that's cut at 400 hertz. So down here, just like with John Atkinson's stuff, the microphone is right on the speaker, and up above 400 hertz, that's what it looks like at 1 meter. So you see a bump up, it's just below 100 hertz at about, it looks like it peaks at about 90. But that's right on the cone. It goes along, it's pretty flat. It does, however, have, at 7K, a nice big bump. And the interesting thing about it is I listened to the speaker and I go, well, I'm not quite hearing the big bump. And in fact, when I went back to Frank and said, it's got a bump at 7K, he goes, really? I didn't measure a bump. I'm going, well, no, it's got a bump. And I've measured it several times. But there it is. It's the same kind of flaw that you see in every full-range speaker in the world that I've ever run into. And it either gets dealt with or it doesn't. In point of fact, I'm running it over there with the bump sitting naked for everybody to hear. But I think you'll find that it's not bad at all, and beyond that, it's very easily dealt with. Out in the room, instead of doing near field on the bass, this is what you see, is the thing starts rolling off somewhere between 100 and 200 hertz, which is typical of about a 6-inch driver in this. But the high Q comes to its rescue at the last moment and gives it some bottom end. So, in point of fact, you listen to it and you go, well, that's pretty decent. In fact, everybody who's heard the thing has gone, oh, I like that. That's pretty nice. You can go over and hear it for yourself or not. The bump at 7K is still there. There is a very simple network that will pretty much can that, and that's it right there. That'll take about 4 to 5 dB off that 7K. It'll still have a bit of a bump, but the bump will be down into a little more reasonable figure. This is part of a philosophy that seems to have emerged over the years of doing everything in halfway measures. You got a bump in a speaker and an equalizer. You can adjust it all the way down to where it's absolutely flat, and you go, well, I don't know, I don't really like that either. But if you find that, you will often find, and this is more typical than not, that if you only go halfway with it, let's say you got a 10 dB bump, you take it down 5 dB and you go, okay, that's good. In fact, it typically will sound better than if you've actually flattened it right out. This is true of so many phenomena in do-it-yourself thing, this activity, that's a really good rule for everything. Do everything in halves. When I adjust bias on amplifiers, I don't adjust it to the value that I want. I go halfway there and let it sit. And same thing with DC offset voltage. I run it halfway to where I think it's going to be, or I might want, and I let it sit. And I keep doing things in halves. Now, of course, you could argue that you'll never get there at all, but to the extent that you do, you're probably going to find yourself on much safer ground. Equalization is one of those phenomena. I had a wonderful AccuPhase digital equalizer where you hit the button and it just flattened the speaker out totally. And I didn't like it that way as much. I found that if I kind of halved weighed it, the flaws against the correction, that I liked that better than either extreme. So I just toss that out. It's so common that it's probably, we could call that the half-pass rule, and there we are. I think.
Apply the half-pass adjustment.
Yes. Okay, any questions on this?
Yeah, where can we get one?
This guy is currently negotiating to get baskets and stuff built, and I expect that he's going to have them out next year. The pricing, preliminary information on pricing is that it's going to be very comparable to the comparable Lowthers. In other words, you can buy a pair of Lowther 6-inch with the ceramics for somewhat less than $1,000 still, and I think and that's a pair, and I think that's about the figure that we're into here.
Can you think of any reasons why correcting only 50% does sound better? Are there artifacts added when you flatten it?
I don't know. I know why I do it with adjusting bias and offset, but why that sort of phenomena is with speakers, I actually just don't know. I just noticed it's there. What that means is that the do-it-yourselfers want to try that for themselves, but it's a real good rule of thumb.
The speakers there have the correction?
The one that's playing there does not. So when you go, oh, I hear that, you can get rid of it easily enough. It's at a high enough frequency that it's not that obnoxious. Your standard full range that I normally deal with have got that bump at 2.5K. This is at 3 times that frequency, so you can, it's what they call the Lowther shout. And it exhibits itself in pretty much all the full range. My V-fets do it also. It's like the only driver that I have that doesn't do it is the now no longer available Pioneer BUFU 20. And But you have to put a tweeter on that in the end, anyways, if you really want to, you know. But it's pretty consistent. Interestingly, if you take the whizzer off of these things, the bump is worse. I found that out because I took the whizzers off of a pair of Louders and the bump went up. So I decided that maybe that wasn't really what the problem was.
Do you know if that's like off axis? Is it still there?
That's on axis. It goes away a little bit off axis. In fact, I usually listen at about 10 degrees, maybe 15 degrees off axis. And so that fixes a lot of louder problems too. You know,
And that was like kind of a beating kind of effect.
it does.
And that would also be why you wouldn't want to overcompensate because that off axis.
Good point. Good point.
Yes, that's good. The halfway would take you
Yeah.
to compromise between on and all that.
No, that's the other thing. I mean, everybody here knows you toe them in or you toe them out or you move them in or you move them back. You want to play with the positioning when you're thinking about all these. There was a question here. He's working on a field coil. John Verhalen at Louder America said, wow, that looks like that would go real good with the field coil that I'm working on too. So it may be that John steps in to help with that. I have no idea. I'm just the guy going, hey, look at this. And somebody else is going to figure out what kind of business it's going to be. Okay, thank you very much. Oh, go ahead.
This is just a basic question. I'm sure it's been answered in previous burning amps. The field coil, is that powered with an AC or DC?
AC, DC. Yeah, it needs to be DC. Otherwise, it sounds funny. Yeah, you don't want that. All right. Well, that is it. All right. Thank you very much.
Very extremely powerful. Maybe that's the.
Oh, one more thing. I have some photos of old product, and I'm happy to autograph if anybody wants them.
Oh wow!
Just queue up.
The one pass on.
Well, now this is nice stuff here.
Some of the finest audio gear ever created by man.
Around my manual.
Well, wait a minute. Okay.
Well, the thresholds.
Those are threshold, but I also somewhere have. Hold on.
One of the really great amps of all time.
Yes, but.
The LF. Yes.
That's right.
Thank you. Wilson.
Yes. Okay.
All right, thank you.
Yep.
Thank you, Nelson.
Sure, I'll take one.
Okay. You have to build an altar for it.
I don't have one, so you can take one. I like to take a picture with you.
Sure. Let me sign some more of these first. Kent, would you like one?
Can I have a threshold?
Yeah, of course.
Why, thank you.
I'll take a threshold. I'd like to own one of these someday.
Oh, well, that's actually technically possible. They occasionally show up on eBay, and we still service them.
Okay, they're no longer made.
Sure. Can I get an LFO? But actually, can I get two of them? One for me and one for Vince Nena.
For who?
Vince, VDI Nena.
Okay.
I would have thought you'd never.
Oh, wait a minute. That was it.
I'll tell you what. I'll take whatever you got.
Well, this is what I got now. You and he can fight over it.
Thank you very much.
Okay.
Oh, I'll take one.
Well, there you go.
Which one is this?
That's a Stasis 2.
Okay. I'm the owner of one of your 200.8s.
Ah.
And it is we're rebuilding our house, so the system is put away, and now we're living in a one-room apartment where I have a stereo coming out of one speaker over my head, and every day it's like pain because I can't. Thank you very much.
Well, that print is 38 years old. I found them in an envelope.
Yeah.
Thank you very much.
Enjoyed it. Thanks for your contribution to the community.
My pleasure.
Sign me one of them things.
Would you like one?
I'll put it in my office.
Thank you.
I'll throw it in the old linear office and very good. Take care of yourself.
Picture?
Oh, absolutely.
Thank you. Oh, I want to ask you a question. So me and Jim were discussing the IF 240. And we were wondering, I was wondering whether you had noticed the VGS range